Between 2021 and 2023, geopolitical conflict shut down traditional trade routes, forcing bulk cargo to divert southward along the western Black Sea. Much of that diverted traffic absorbed directly into a single bulk cargo pier at the port of Constanta in Romania. On paper, this was a manageable surge. Port logs recorded a vessel traffic increase of roughly 35% over the 2-year period. This chart plots annual expenses in blue against CO2 emissions in red. Despite a 35% traffic bump, congestion-related emissions spiked over 800%. Looking at the blue bars, operational expenses simultaneously grew fivefold, reaching €10.6 million by 2023. Under tightening European regulations, these logistical delays now trigger immediate and quantifiable financial penalties. A linear 35% increase in traffic triggered a nonlinear, catastrophic failure in both port efficiency and environmental compliance. Yet, according to the port's own internal data, the pier remained theoretically stable throughout the entire crisis. To understand this, we look at the system utilization rate, ROE. It measures incoming traffic intensity against maximum capacity, where 1.0 is absolute failure. Throughout the 2023 surge, Constanta's utilization peaked at 0.90, never crossing the mathematical failure threshold. To deconstruct this illusion of capacity, we have to apply advanced queuing models to the raw vessel data. When maritime infrastructure operates just below its maximum theoretical limit, it is dangerously exposed to even minor fluctuations in demand. Researchers evaluate these bottlenecks using the M/G/1 queuing model: random Poisson arrivals, general service times, a single pier, and infinite capacity. System utilization is calculated by dividing incoming vessel traffic rate, lambda, by average service intensity, mu. This graph charts historical port data. The green line shows system utilization climbing from 0.52 to a critical 0.90 threshold. Meanwhile, the red line, average waiting time, does not scale proportionally. Instead, it rockets from 87 to 788 hours. In physical terms, an average wait time of 788 hours means a cargo ship sat completely idle at open water anchorage for roughly 33 days. This exposes the specific bottleneck mechanic of a single berth configuration. Once utilization exceeds 0.85, the system loses all its slack. It can no longer absorb variance. Because the berth allocation is fixed, there are no parallel service points to offload excess demand. Every minor delay in cargo operation cascades directly onto the next waiting vessel. In a rigid queuing network, time does not scale linearly with traffic. It compounds exponentially against the queue. That exponentially compounded time now falls under strict European regulatory frameworks, specifically the EU Emissions Trading System and Fuel EU Maritime rules. These frameworks transform vessel idle time into a direct carbon liability, taxed according to the ship's specific fuel consumption and emission profile. To maintain auxiliary power, heating, and crew systems while sitting at anchor for 33 days, a ship must continuously burn marine gas oil. The queuing model converts those hours stuck in the queue into fuel consumption. Burning 1 ton of fuel generates 3.206 tons of carbon dioxide. To calculate the penalty, we multiply that CO2 tonnage by the UETS allowance fee, €87 per ton. For Constanta's single bulk pier, the emissions generated strictly by queuing delays equated to €2.38 million in carbon compliance costs for the year. Logistical efficiency now dictates a terminal's baseline exposure to carbon markets and its ability to maintain competitive fees. To quantify the fragility of operating at a 0.90 utilization rate, researchers subjected the port's operational model to a 1,000-iteration Monte Carlo simulation. The simulation injected minor stochastic variances into 2 everyday parameters: vessel maneuvering times, ranging between 1.5 and 3.5 hours, and entry safety intervals between berthings. These fractional changes mimic standard, unavoidable port realities, like a sudden shift in wind direction or a brief delay in tugboat availability. This scatterplot maps system utilization against extreme CO2 emission spikes. The median outcome sat near 3,000 tons. But as utilization inches toward 1.0, data points scatter aggressively upward into a sharp exponential curve, pushing emissions past 350,000 tons. These extreme outliers serve as mathematical stress test boundaries. They prove that high utilization infrastructure is always one minor operational disruption away from collapse. Because geopolitical and economic demand shocks are inevitable, physical infrastructure capacity alone cannot insulate a port from these nonlinear risks. The first necessary intervention targets the emissions variable directly through a technology known as cold ironing. Cold ironing allows berthed vessels to shut down their onboard auxiliary combustion engines entirely, plugging in to run their cargo operations directly off the local shoreside electrical grid. By electrifying the cargo handling phase, models show the pier's total emissions and its corresponding EU ETS liabilities would drop by nearly 37%. While shoreside infrastructure requires a capital outlay of up to €6 million, the potential to offset over €2 million in annual carbon costs makes it a strategic priority for terminals operating near capacity. Cold ironing acts as a powerful structural firewall, successfully severing the link between compounding logistical delays and regulatory carbon penalties. The second necessary intervention targets the time variable directly through just-in-time arrival protocols. Just-in-time utilizes predictive digital scheduling to instruct ships to reduce their transit speed days before reaching their destination, preventing the physical queue from forming. Slowing down at sea is exponentially more fuel efficient than rushing across the ocean at maximum speed, only to sit idling at anchor for a month. This requires abandoning the outdated concept of ports as static physical assets and rebuilding them as dynamically managed digital transit nodes. This integration of queuing theory and carbon pricing defines the operational baseline for European ports navigating the Green Deal. In a highly regulated, stochastic world, theoretical capacity is meaningless. Mastering the nonlinear math of the queue is the only way global maritime trade can operate.